Welcome to CECS 228. In this lecture video, we're going to pick up on Relations Part 3 lecture notes, specifically on page 6. So we last left off on equivalence classes and partitions, and we're going to start by taking a look at the definition of partition. So a partition of a set S is a collection of disjoint, non-empty subsets of S that have S as their union. And we can see here a little diagram of what that might look like. If this whole oval represents all elements of the set S, then we've separated into regions different elements of the set. So presumably there are elements in each of these regions, and none of those regions overlap, which means that they are disjoint. And if we take the union of the regions, then we would get all of the elements of the set S. So to see something a little bit more concrete, let's look at example number 8. This one is asking, what is one possible partition of the set S which contains the elements 1, 2, 3, 4, 5, and 6? So that means that we are simply going to break up the whole set into subsets, non-empty subsets. So one possibility could be, for instance, having a set, let's call it A1, that contains the elements 1, 3, 5. Another set, we'll call it A2, that contains the elements 2, 4. And the final set, we'll call it A3, that contains the element 6. And so, as you can see, these are disjoint. They don't share any elements in common. And if we take the union of the three sets, then we would get the original set S back. Alright, so with that in mind, let's look at the following theorem. The theorem says, let R be an equivalence relation on the set S. So that means that the relation has to be reflexive, it has to be symmetric, and it has to be transitive. And we can think of S as being our domain. Then the equivalence classes of R form a partition of S. Conversely, given a partition, so this is the set of sets. We're calling each set A1, A2, all the way down to maybe AN. So given a partition of the set S, where I is a set of indices, so this is just containing integers, we'll say 1, 2, down to n. So these are the indices of the subsets of S. There is an equivalence relation R that has the sets AI as its equivalence classes. Okay, so what this is saying is that, for instance, here we came up with a partition of S. What the theorem is saying is that we can use these subsets to form an equivalence relation, because these individually are the equivalence classes of an equivalence relation. And so let's take a look at example 9. This one is asking us to list the ordered pairs in the equivalence relation R produced by the partition A1, which contains element 1, 2, 3, A2, which contains elements 4 and 5, and A3, which contains the element 6. So we're going to go ahead and take a look at how we can approach this. According to the theorem, each of these subsets is an equivalence class. Right? These are equivalence classes of R. So I'm going to take this first one, A1, and I'm going to say that I'm going to pick a representative. Okay, remember, in an equivalence class, it's just a set of elements. We can pick one of the elements as the representative, and there is nothing special about the representative, so it doesn't matter which one we pick. I'm just going to pick element 1 to be a representative of that class, and I'm just going to say this is the equivalence class containing elements 1, 2, and 3. And now, if it's a class, that means that this element 1 is going to be paired with every single element of the set. Okay, so we're going to get ordered pairs 1, 1, 1, 2, and 1, 3. Okay. But now let's think about what it means for a relation to be an equivalence relation. It means that it has to be symmetric. So for each of these pairs, I'm going to have the ordered pair that switches the two elements. So I'm also going to have the pair 2, 1 and 3, 1. Yep. Now we said we chose 1 as a representative of the set, but we could have also chosen 2. And because again, there's nothing special about it. So that means that if we would have chosen 2, 2 would also need to be paired up with all of the 3 elements that are part of the set. So we would get 2 paired with 1, 2 paired with itself, 2, 2 paired with 3, and then we would get all of the elements that are the, well, the symmetric pair, or the symmetric pair to 2, 1, which in this case would be 1, 2, and we already have that here. Then for this one it would be 2, 3, which we don't yet have. We don't yet have 3, 2, so we're going to write that one down. Okay, and then if we pick 3 as the representative of the equivalence class instead, that means that 3 needs to be paired up with all of these elements. So we would have a pair 3, 1, which is already here, then 3, 2, which is already here, and then 3, 3, which we haven't listed, so we're now going to include. Alright, so this is from the set A1. We're now going to do the same process with A2. I'll take a representative, let's say 4 initially. And so the equivalence class of 4 is the set with 2 elements, 4 and 5. That means that 4 has to be paired with itself, and it has to be paired with 5. Now, since R is an equivalence relation, it has to be symmetric. So that means that we're going to be taking, we're going to commute the 2 elements to get 5, 4. Alright, and then instead of picking the 4, I'll now pick the 5 as a representative, and that means that we need to have an ordered pair 5, 4, which we already have, and an element 5, 5, which we don't yet have. So I'll write down. Okay. Last one, A3, there's only one element, so that's the one that we'll choose as a representative. The equivalence class of 6 is 6, so that means that we'll have 6, 6 as an ordered pair. And that's the only possible ordered pair that we can get out of that equivalence class. So what that means is then that the relation is going to consist of all of these pairs. Because now, well, we need to make sure that it's reflexive, so it should have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6, which would do. The next thing would be that it needs to have, for every ordered pair, it needs to have the symmetric pair. So if I have 1, 2, I should have a 2, 1. If I have a 1, 3, we should have a 3, 1. So on and so forth. And then it should also be transitive. Now, I'll let you guys kind of check that this is indeed transitive, but the reason why it's always going to result in a transitive relation is because we are forming ordered pairs within these subsets. So any combination of 2 ordered pairs will result in another ordered pair that is still part of this subset. So in the end, you're just going to get ordered pairs that are part of the relation. Okay, let's take a look at example 10. This one reads, let R3 be the relation from example 5. So let me go to example 5 for a second. Example 5 was the relation Rn over, where n is some positive integer and s is a set of strings. Rn is the relation that takes 2 strings and pairs them together if and only if the 2 strings are the same, or if both S and T have at least n characters and the first n characters of S and T are the same. Okay, so that's the one that they're asking us to consider. The question is, what are the sets in the partition of the set of all bit strings arising from the relation R3 on the set of all bit strings? Okay, so let's take a moment to digest what this is asking for. They want us to find what are all the sets that are going to partition the set of all bit strings. Okay, so if we think about what R3 does, R3 takes two strings and pairs them together if both strings have the same first three bits. Okay, so I'm gonna represent that by saying string S is bit 1, bit 2, bit 3 with some other bits. Okay, we'll just call S4 down to Sn, where n is the length of the first bit. And T will also have the same first bit, B1, B2, B3, and then the fourth bit might be something different. So T4 all the way down, let's say to Tm, where m is the length of the string T. Okay, that's what R3 does. That's the type of elements that are part of R3. So if we want to look at a partition is that is going to be determined by the equivalence classes of R3. So ultimately we want to figure out how many different equivalence classes can arise. Okay, so let me just write that here. So i.e., what are the equivalence classes of R3? Now to determine that, well, let's think of how many different bit strings we can have of length 3, because ultimately that is going to define the type of pairs that we can create. So what I mean by that is one bit string length 3 could be like 1, 1, 1, right? And any two bit strings that begin with 1, 1, 1 would get paired together, which means that that would form an equivalence class, right? 1, 1, 1 under R3 is going to have a set of strings, maybe let's say 1, 1, 1, or 1, 1, 0, or 1, 1, 1, 0, 0, so on and so forth, right? That's one equivalence class of R3. Another equivalence class that we can obtain comes from the bit string with the 3 bits 1, 1, 0, right? Because then that is going to now form a distinct set of elements, a distinct set of bit strings that begin with 1, 1, 0. So 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, maybe, and some, the rest of the bit strings, all possible bit strings that begin with those 3 bits. Okay, what's another one? Well, we could also have 1, 0, 1 under R3, or we could have 1, 0, 0 under R3. Another one could be a 0, 0, 0 under R3. We could have a 0, 1, 0. We could have a 0, 0, 1. And a 0, 1, 1. We're now going to take a look at partial orderings, starting with the definition. A relation R on a set S, we should have an S here, is called a partial ordering if it is reflexive, antisymmetric, and transitive. A set S together with a partial ordering R is called a partially ordered set, which is denoted S, R. Okay, so let's exemplify this with example 11. It reads, show that the relation R of ordered pairs A, B, where A is greater than or equal to B, is a partial ordering on the set of integers. Okay, so we have to check three things. We have to make sure that it is, first of all, reflexive. Next, that it's antisymmetric, and finally, that it's transitive. So first, let's check for reflexive. We're going to take any two, or any integer, because this is over the set of integers. So for any integer or I should write A is greater than or equal to itself. Hence, we are going to have that A will be part of the relation. So that means that it is reflexive. Next, we want to take a look at whether or not it's antisymmetric. And so now we're going to take two integers, A and B. So for any two integers, A and B, if we have that A, B is part of the relation, and B, A is part of the relation, then that means that the first ordered pair has to satisfy that A is greater than or equal to B. And the second order pair has to satisfy that B is greater than or equal to A. So if A is greater than or equal to B and B is greater than or equal to A, that means that A and B have to be equal. And that's exactly the definition of antisymmetric. It says the only way that A, B and B, A can be part of the relation is if these two are equal. Otherwise, it's not antisymmetric. Okay, so in this case, this means that, yes, it's antisymmetric. And finally, is it transitive? Well, let's see. For any three integers, A, B, and C, if we have A, B being part of the relation and B, C being part of the relation, then that means that A should be greater than or equal to B, and B should be greater than or equal to C. So now, if A is greater than or equal to B and B is greater than or equal to C, that means that A has to be greater than or equal to C. And if it satisfies that condition, then that's enough for the ordered pair A, C to be part of the relation. So that means that it is transitive. And so since it satisfies all three requirements of a partial ordering, R is a partially ordered, it's a partial ordering, or if we're talking about the set of integers S along with the relation, that's considered to be a poset. Okay, so we'll write that down. This means R is a partial ordering. And the set S along with the relation R is a poset. Example 12 is very similar. It's asking, show that the inclusion relation subset with potential for equality is a partial ordering on the power set of a set S. Okay, so before we try to check anything, let's try to write explicitly what the relation R exactly is. The relation R is the ordered pair of two sets, okay, A, B. A and B, such that A is a subset of B, and both A and B are in the power set of S. And that's the relation that's being described here. And we want to figure out whether that relation is going to satisfy being reflexive, first of all. Okay, so is it reflexive? Well, let's consider any set that is part of the power set of S. Since A is a subset of itself, then that means that A will be paired with itself, and it's going to be part of the relation. So is it reflexive? The answer is yes. Is it antisymmetric? Okay, again, we're going to take any two sets, A and B, that are part of the power set of S, and take a look at what it means for A to be, well, actually, let me write it this way. If A comma B is part of the relation, and B comma A is part of the relation, then that means that A is a subset of B by definition of R, and B has to be a subset of A, again by the definition of R. Now, we've seen before that when A is a subset of B and B is a subset of A, that is the definition of equality for two sets. So this implies that A is equal to B. And that is also the definition of antisymmetric. The only way that the ordered pairs AB and BA can be part of R is if A is equal to B. The answer for this one is yes. And finally, is it transitive? Well, now let's take any three sets that are part of the power set and take a look at what it means for AB to be part of R and BC to be part of R. And so if they're part of the relation, then that means that A has to be a subset of B and B has to be a subset of C. And so just to draw a diagram, if this is B and A is a subset of B, and in this case we have an even larger set, let's call it C, that contains B, well then automatically it needs to contain A as well. Okay, so this implies that A is a subset of C. And that means that we also have the ordered pair A comma C as part of the relation. So that means that this is transitive, and as a result, we have that R is a partial ordering, and the set, which in this case, or the domain that we're considering, is the power set of S. So the power set of S together with the relation R is a poset. Let's take a look at an example of something that is not a partial ordering. So in example 13, we have a relation R on the set of people such that X comma Y will be part of the relation if X and Y are people and X is older than Y. And well, they want us to show that this is not a partial ordering. So again, before we check any of the conditions, let's just write out explicitly what R is. R is the set of ordered pairs, or X comma Y, where the age of X is going to be greater than the age of Y. And the domain for X and Y is a set of all people. So X and Y, I'm just going to call this P. Okay, so it's for the set of people. Alright, so we have to show it's not a partial ordering, so we want to check which of these conditions are going to fail. Let's check for reflexive. Uh, for any person who is, well, part of the set P, so let's just call it X. For any person X, well, the age of X is not going to be greater than the age of X, right? Meaning no one is going to be older than themselves. So that means that the element x comma x is not going to be part of the relation. And so if it's not part of the relation for any x, it means it's not reflexive. And this is the main reason why this is not a partial ordering. Okay, so that brings us to the definition of comparable. We're going to let A and B with this symbol, which means precede. So we're going to let A precede B with the possibility that they are equal. To note the statement that A comma B is an R and an arbitrary poset S comma R. The elements U and V of a poset are called comparable if either U precedes V or V precedes U, with the possibility that maybe they're equal. When U and V are part of the domain, when they're part of S, but neither U precedes V nor U, and I think this is a typo, nor V precedes U, then we say that U and V are incomparable. Okay, this is also a typo. Okay, so let's take a look at this, some concrete numbers. Example 14 is asking, is the poset that consists of the set of positive integers with the divides operation. So in that poset, are the integers 3 and 9 comparable? Are 5 and 7 comparable? Okay, so first let's write what relation we have here. Okay, so this is written a little bit different. Like they didn't write explicitly what R is. It's just they just wrote what operation R is using to determine whether two elements can be paired and be part of the relation. So the relation here is the set of all ordered pairs A comma B such that A divides B, where A and B are both positive integers. And now they're not asking us to check whether this is going to be a partial ordering. They're already telling us that it's a poset. What they want us to check is whether 3 and 9 are comparable and whether 5 and 7 are comparable. Okay? And so if we look at the definition here, they're going to be comparable if A comma B is part of the relation. So in terms of 3 and 9, 3 divides 9 because 9 is 3 times 3. So that means that 3 comma 9 is part of the relation. And so what that means is that 3 is comparable to 9. Specifically, 3 precedes 9. Now, if we look at 5 and 7, 5 does not divide 7, right? In fact, 7 is prime. It's not divisible by any other number. So that means that 5 comma 7 is not part of the relation. And that means that, well, not only that, but also if we think about 7 dividing 5, that doesn't happen. So also 7 comma 5 is not part of the relation. Okay. So what we have then is that 5 does not precede 7 and 7 does not precede 5. So because neither of those we can't make a claim of precedence for in either order. We say that these are not comparable. Okay, so 3 and 9 are comparable, but 7 and 5 are not comparable. Now, when every two elements in the set S are comparable under some partial ordering R, we actually call it something different. We call it a total ordering. And then there are other definitions that result from R being a total ordering, and that is the operation under which the elements are comparable is called a total order. Then the set S is going to be called a chain, and the poset, which remember is the pairing of the set S with the relation or with the operation that defines the relation, is set to be totally ordered. So let's take a look at example 15. They're asking us, is the poset with the set of integers under the operation of less than or equal totally ordered? Okay, so the first thing that we need to check is if it's going to be comparable for any two elements. Okay? Or rather, that's the condition that we have to check. If for any two elements that we pick, if they're going to be comparable under this partial ordering. Okay, so let me just write the partial ordering. The partial ordering is all elements a comma b such that a is less than or equal to b, where a and b are integers. Now, we're going to take any two elements. We'll call them x and y that are part of the integers. Okay. And three possible scenarios can occur. The first one is that x is strictly less than y. If x is strictly less than y, then we have the ordered pair x comma y in R, which means that x is going to precede y. If we have instead that x is greater than y, then we have that the ordered pair y comma x will be part of the relation. And in that case, y will take precedence over x. And finally, if x is equal to y, well, that means that we still have the ordered pair x comma y as being part of R. So that means that x will take precedence over y. So we can see that in any of the three possible cases, x and y are comparable, right? And this is arbitrary element, so it means that it works for any two integers that you can that you pick. Okay, so hence any two elements which are supposed to be integers, so any two integers are comparable under R. And this makes the poset a totally ordered set. Yep. Okay, let's take a look at example 16. Is the poset the set of integers with the divides operation totally ordered? Well, again, we've seen this relation before. This is the set of all ordered pairs such that A divides B. where a and b are integers? And the answer here is no, because we already saw from example number, what was it, example number 14, that 5 and 7 were not comparable. So the answer here is z with the divides operation is not totally ordered because we're just using one example. 5 and 5 and 7 are integers, but 5 cannot be compared to 7, and 7 cannot be compared to 5. We're going to take a look at one last example, example number 18, which reads, is the set of ordered pairs of positive integers z plus cross z plus with ordered pair a1, a2 taking precedence over the ordered pair b1, b2. If a1 is less than b1, or if a1 and b1 are equal, then a2 is less than or equal to b2, well ordered. So there's quite a bit there that we need to unpack. Let's start by looking at what is the relation. Okay, the domain of the relation is z plus cross z plus. So we're actually taking pairs as elements in the ordered pairs of R. So what I mean by that is the following. R is the set of ordered pairs P1, P2, where P1 is equal to A1, A2, and P2 is equal to B1, B2. And on top of that, we have that A1 will be less than B1, or we'll have that A1 is equal to B1 and A2 is less than or equal to B2. Okay. So just to give an example of an ordered pair that would be part of R, if we have the ordered pairs, let's say 1, 3 and 2, 3, okay, then these two together would be part of the relation R, because the first coordinate is less than the second coordinate. And so it satisfies this condition. So that means that these would get paired together. Here's another example. Let's say we have an ordered pair 5, 2 and 5, 1. Okay. Well, in this case, the first coordinates are the same, but for the second ordered pair, the second coordinate is less than the second coordinate of the first pair. So that means that we would have the ordered pair 5, 1 paired with 5, 2 as part of the relation. Or to write it a bit more nicely so that we don't have ordered pairs within an ordered pair, we write it as 1, 3 takes precedence over 2, 3, and in this case 5, 1, I'll write it down here, 5, 1 takes precedence before 5, 2, or precedes 5, 2. Alright, so that's the relation that we're dealing with. By the way, this ordering of these elements is also called lexicographic ordering. We'll write it here. Okay, so they're asking us, will the a set of positive integers cross itself be well ordered under this relation? Okay, so there are a few things that we would need to check that I'm going to actually leave for you as exercise, these first parts. The first thing that we would need to check is that z plus cross z plus with r is a posit. I'll say yes without showing the full justification for it, but I'll leave that as an exercise for you. Okay. The other thing that we need to check, now that we said okay, yes, it's a posit, we have to check whether it's totally ordered. Okay, and that we'll go through together. So let's just take any two ordered pairs that are part of this set. Okay, so for any ordered pair, let's say A1, comma A2, that is in Z plus cross Z plus, and in fact, let me just write them, both of them here. Okay, so we have two ordered pairs, B1, B2 would be the second one. Are these two elements going to be comparable? Well, let's see what type of situation we can encounter. We could either have that A1 will be less than B1. Okay, this is one possibility. In such a case, that means that A1, comma A2 will precede B1, comma B2. Yeah. Because by definition, if R, it's going to satisfy this condition. So we'll have this order. The second possibility is that A1 is greater than B1, in which case B1, comma B2 will precede A1, comma A2. Okay, the next possibility is that they are equal. And if they are equal, that means that we now take a look at the second coordinates. So we might have equal first coordinates and then A2 be less than B2. And if that is the case, then that means that A1, comma A2 will precede B1, comma B2. Because according to the lexicographic order, if A1, comma B1, if A1 equals B1, then and A2 is less than or equal to B2, then we have the first pair in the first coordinate, and then second pair in the second coordinate. Or in other words, the first pair precedes the second. Okay, the fourth possibility is that A1 equals B1 and A2 is greater than B2. Okay. In which case, we'll have that B1, comma B2 will precede A1, comma A2. Okay. And we have one more possibility. Let's see, I think I can fit it in here. The last possibility is that A1 equals B1 and A2 equals B2. Well, in that case, what should happen? We go back up here, A1 equals B1, and then A2 equals B2, then we still pair P1 with P2, where P1 precedes P2. So that means that we'll have A1, comma A2 preceding B1, comma B2. And so for any possibility, we are able to compare the two pairs, and that means that this is totally ordered. Now, the second condition that we need to check is that every non-empty subset of S has a least element. Now, S in our case is Z plus cross Z plus. So we need to make sure that if we take any subset of that set, that there will be a least element that is part of the set. So what we're going to do is we're going to consider a subset. We're going to call it A. So consider A, which is a subset of Z plus cross Z plus. Does that have a least element? Well, the answer is yes. The least element will be the ordered pair I'm going to call it A min comma B, such that A min is less than or equal to, actually strictly less than X for any other pair. Let's call it X comma Y, that is part of A. Now, if you have more than one ordered pair that have A min as a first coordinate or first element of the pair, then we look at the second element and find which one is the minimum out of those pairs that share in common A min. Okay, so we'll write that. If there exists more than one ordered pair with A min as a first coordinate of the pair, so for instance, let's say that we have A min comma B1, A min comma B2, all the way down to A min comma Bm. So there are m potentially ordered pairs that all have A min as the first element of the pair. Then the least element will be A min comma B min, where B min will just be the smallest out of all of these second coordinates, where B min is less than or equal to Bi, for I being 1, 2, all the way down to m. Okay, so A is some arbitrary subset. It doesn't have anything special about it. The only thing is that it's non-empty. So for any non-empty subset of Z plus cross Z plus, we're going to be able to follow through the same argument, which means that all subsets of S that are non-empty have a least element. And so now both of the conditions for a well-ordered set are met, which means that Z plus cross Z plus is well ordered. Under the relation R.